Michelle. Thank you. Well, because I saw the exposure research, I did put together a talk that's a little bit of an overview of exposure challenges with studying fires. Here we go. Maybe I'll come over here. I see. Okay. So the first thing, as I said in my previous talk on the epidemiology, is that we often are studying these after the fact. And when we're looking retrospectively, the first question is, well, which population areas were exposed? And so some of the early research would do a temporal comparison. And this is an example where on a study I was looking at, we decided to look at the air basin, because California has these nice air basins. And so we looked at the South Coast Air Basin, but note in this yellow area outlined here that we saw that there are fires even outside of this air basin. We could have included some other air basins as well, but even within the air basin that we chose, we could see that for this exact time point, the wildfire smoke plume was going through part of the air basin, but not affecting all areas equally. However, for this study, we decided to go forward, and then we had to think about, well, when was the fire? And we have a start date for every fire, but then when you think about the smoke impacts, if you look at, we know when there's a date on when the fires were contained, but even when they're contained, that means they can still be smoldering, and there can still be a lot of smoke impacts. And so when you set that end date is actually quite challenging, especially in a situation like this where we weren't actually monitoring the air quality and getting an estimate of the air quality. And so we made an estimate of when we looked at some of the monitoring data to see when it ended, and we created this time period. And then we just did what I said here is just a temporal comparison, right? We didn't actually quantify the exposure. And a lot of the early studies on wildfire health impacts have done this, and they still find some significant associations. But some of the drawbacks is that it doesn't get at the dose response. We don't know for how much, for a certain amount of increase in, say, PM 2.5, what's the associated health response. And then, as I said previously, to answer a question, that the associations might not just be due to the smoke, right? There might be other exposures that are related to the fire, such as the sort of fear and the anxiety that is produced with these fires. So increasingly, people want to actually quantify the smoke exposure. And so the first place to turn is monitoring data. And there's a lot of this available. You can go to the EPA's website and you can download the data. And same with CARB has a lot of its own monitors and are relatively easy to access. And that's wonderful. You're getting actual measurements from validated monitors for the actual exposures. But some of the challenges with looking at the monitoring data is that they're not always in the locations you want. The monitors that the EPA puts out are often in urban areas, which is not always very close to where the fire is actually burning. So you're getting sort of farther downwind. I always think about this, when we look at a smoke plume, it's not well mixed, which tends to be what we're looking at. We're looking at other exposures of air pollution, sort of like the point and mobile sources in urban areas. We're trying to get sort of that background level with the EPA monitors versus a wildfire. The exposures under the smoke plume can be very, very high, and then not too far away, they're much lower. And so if you look at an image like this one on the right-hand side there, if the monitor for that, say there's one monitor in this metropolitan area, and it was right under that smoke plume, but it was assigned to everyone, on the other side of that water body, you'd be assigning a very different exposure than they were actually exposed to, or vice versa. Say the monitor is far from the smoke plume, but you have a lot of people who are right under it, you could be giving them an incorrect exposure. A lot of the EPA monitors for PM 2.5 don't measure every day. They measure every third or sixth day. There's the federal equivalent monitors, which tend to be more likely to report every day. But when you only have every few days, you're missing information, and we know that the wildfires can spike and change quite a lot day to day, and so you don't want to just interpolate and miss that spike or miss a really low day in between two really high days, because the smoke plume can really move quite a lot on small time scales. I've looked at satellite imagery of a smoke plume that's captured every half hour, and you can just see this sort of meandering plume due to wind patterns and such. So we can lead to exposure misclassification. And this is just an example for Sacramento I got from the EPA. That's where the EPA monitors are. It's quite a large city. If we assigned everyone to their nearest monitor and or the average, a lot of studies have used sort of the average across a metropolitan area for the monitors, we'd probably be missing exposure if there was a wildfire going through there. Even in Southern California, where you have a much denser set of monitors, this is an image from a paper by Wu et al. From 2006, looking at wildfires in the South Coast Air Basin. There's lots of monitors. Those are the black circles with the white dots, but you can see that dense plume, and it's not uniformly distributed, and some of the monitors are going to capture it and some aren't. But even some people might be closer to a monitor that's very different from their exposure. Although I do want to say here, Wu did a very complicated exposure assessment in that paper. That's not, that was just an example to show the differences between a really dense plume and where the monitors are. So increasingly, researchers are turning to things like satellite data, which is a measurement of well, there's a few different satellite products. The one I'm going to talk about mostly is aerosol optical depth. So aerosols is just another term for particles. And what this measures is the satellites measuring how much of the solar radiation we would expect to be reflected from that pixel on the Earth is actually getting to the satellite, and assuming that everything that's not getting there is being reflected by the particles in the atmosphere. And so what's great about this is that the number of products available has, there's the MODIS AOD, which is twice daily. It was at 10-kilometer resolution, but you can get the MAIAC data, which is now at 1-kilometer resolution. So we're getting better and better data on aerosol optical depth from satellites. There's also some stationary satellites from the GOES satellites that you can get for multiple time points throughout the day. But a drawback of the satellite data is that it's a full column measurement. And so it's, if the smoke is aloft, very high, it'll be picked up by the satellite, but it won't actually be what the people are breathing. And this is also true for some of these. There's also smoke polygons that are drawn by an analyst at NOAA who looks at the visible imagery from the satellite and draws sort of polygons and denotes whether it's heavy smoke, moderate smoke, or light smoke. And it's used in a lot of epidemiological studies, but sometimes we can see that that smoke is aloft. Oh, I have to go so fast. Okay. So there's also cloud masking issues. Increasingly, researchers are using models, which I think is what Michelle Bell was talking about. And the benefits of this is that you can also sort of set your geographic area and get full coverage. But the and one thing that's really cool about it that a lot of researchers have done is it allows to estimate the counterfactual. You can run the model with all the emissions, including the wildfires, and you can run it without the wildfire emissions. So you get the what would the air quality have been had the fires not happened. And then you can sort of do some subtractions there to get the wildfire-specific PM 2.5. And so that allows for that. But the disadvantages are is that the model output can be really different from the monitoring data because it depends on our understanding of the physical transport and the chemical reactions of the air pollutants. And in my talking to the atmospheric chemists who run these models is that one of the biggest uncertainties is the emissions from the fires. How much air pollution is being emitted from the fires, because it depends on the temperature of the fires, and where in the atmosphere. Is it being injected really high, or is it more at ground level? And so that's why when you compare it with the monitoring data, sometimes it's different. So increasingly, people are trying to combine these. We call these either, you'll see hybrid models or blended models, where we statistically combine information from models, satellite data, and monitoring data, sometimes also with other data as well. So two methods, there's a lot of ways that researchers combine these together. I'm just going to mention two of them here. One of them by a group from Colorado State. They use geographically weighted regression. And then a method that I've piloted and others have used as well, using machine learning to combine all of these data. And just to talk about this a little bit more, basically what we're doing is we have monitors. We know the observation, we know what the concentrations were at that location in that point in time, and we can use auxiliary information nearby, see how it's related, see the relationships there and use it to predict in places where we don't have measurements. This was originally the idea behind land use regression. Those tend to just be spatial models, so I've added spatiotemporal data to get, using meteorology, chemical transport outboard satellite data to get daily estimates, and we don't assume a linear regression. We use a lot of algorithms from machine learning. So just to speed through, we get pretty good output. This is with PM 2.5. My group has also done this. It's under revisions right now for ozone. And then in addition, the group that I've started at the University of Colorado, we're trying to create a large data set using this type of modeling for the Western US for an 11-year period, daily estimates of PM 2.5, and really trying to capture the wildfire. So we've gathered other monitoring data that's not just the EPA data, but includes monitors put out by the Forest Service during wildfires. And we're running the models for fire-affected and not fire-affected days because the relationships between the predictor variables are very different in the two areas. And we're hoping that that will be available to all researchers. We're hoping to put it on an open data platform for everyone to use once we get that out. So the strengths of this is we can combine the strengths and weaknesses of different data sources to get better estimates of air quality that can be used for epidemiological purposes. It does rely on the assumptions that the relationships that we see where we have monitors hold in other locations and at other time points. We don't always take into, there's errors in these models that we need to take into consideration when we do the epidemiological models. Also, there's a few studies that have compared exposure assessment methods and found that depending on what exposure assessment methods, sometimes you can get different results in your epidemiological studies. This is just two papers. One compared, the TOM there is the monitoring, CalPUF is a dispersion model, smoke are these polygons from the satellite that denote where the smoke plumes were, and they found quite different results in that study depending on which exposure model they used. A more recent study by a group from Colorado State, they compared a chemical transport model, Krieged monitoring data, and a regression model that combined those together along with satellite data. And they found for some of the health outcomes, you don't see too much of a difference in the outcomes, but for some of them you do, for example, for COPD and for pneumonia. And then there's a newer paper that didn't find too much difference between using monitored data and modeled data in their epidemiological analysis by DeFlorio Barker et al. So moving forward, I think we need to do more exposure comparison between these exposure models. I think there needs to be more integration of the error associated with the models into the epidemiological models. There's also something that I didn't get a chance to talk about due to time, is that there's a paper, there's at least one paper, I think there's another one out that's looked at social media data. So this Ford paper is looking at Facebook posts of smoke, and they've found that it actually does a better job than some of the satellite data because they consider it sort of like on-the-ground monitors with each person who in that case it's Facebook posts. There's another one with tweets, but they could also, maybe we blend that in, right? We're blending that with all these different data sources, all which have strengths and weaknesses. And then there's this movement towards getting cheaper sensors and or personal monitors and possibly incorporating that. So, thank you.